first we'll have to create a file for the rotation matrix before doing anything. So let's create the file for the rotation matrix in the MATLAB environment. So over here this is given, and we need to type down entire equations of motion. As I have already showed you, phi, theta, psi, they are the Euler's angles, and we will access the Euler's angles from our model and then pass through this matrix and then see how our system is behaving. So first we will create the rigid body dynamics inertial frame to body frame rotation matrix. So let us do it. Now quickly write this function, which is direction cosine matrix, in the rotation form, and we can use that in later on videos or in later on files if needed. Okay, and we can directly use this function if needed to transform from earth frame to body frame and reversely from body frame to earth frame. So basically let's define the function, and called as DCM will be the output, and direction cosine matrix function, and will have the end of the function. So this is what it is. Output will be direction cosine matrix, and input we need is Euler angles. So phi, theta, psi, the input we need from this direction cosine matrix. So we will call it, say, DC, and DC is our variable which is having the Euler angle phi, which is DC1, first element of DC, which we'll define later, and then theta, which is second element of the DC, and then we have psi. So basically we have three elements in this DC, and we are going to use these phi, theta, and psi to calculate the rotation matrix or direction cosine matrix DCM, which will be in vector form. So first of all, we do not need to print these things, so we will use semicolon behind, and then after that we will write the direction cosine matrix based on this equation, this green highlighted equation. We will write it down. So I'll quickly pass the video and write all these equations and then show how it will look in the MATLAB. So now this I have completed how to write it. Let me tell you the way to write it. First you need to go to the formula, and same to same you need to type over here. Our variables are phi, theta, and psi. So you need to type the same phi, theta, and psi. And then for the comma, for the space, for the new column of this matrix. So this is the new column, second column, and then this is the third column. Similarly, for the row, creating new row, we have a column over here. That means new row is created, and this is the new row. In the new row we have this phi, theta, and psi, and so on. Based on this we will get the direction cosine matrix, which is our output. Now to see our program is working fine or not, what we will do, we will not access this variable. We will just simply give some numbers to this phi, theta, and psi, and then see how the direction cosine matrix is giving the output. Say phi is, we are giving no angle in radians, and for the theta we are giving, say, 2 degrees. So we need to convert into the radian, pi by 180, because everything is in radian. So now pi by 180 convert 2 into radian. So now 2 degrees it is giving the output. So we want to see how the output of direction cosine matrix, which is DC, will give. So we'll run this. First we'll have to save this, and this is the same function, so we'll saving it. Now this is what it is giving. So what it is giving is, this is what it is giving. As you can see over here, this is the direction cosine matrix for us in this case. If we give no rotation, then this will be identity matrix. It should be an identity matrix. So let us run for this, and this is coming as an identity matrix. That means everything is working fine. Whatever we have prepared for this direction cosine matrix function, everything is looking fine and everything is fine. Now we'll complete this direction cosine matrix by using the variable DC. Okay, so this is what is the direction cosine matrix is all about.